Hi there, this is Zhiqi, and for my culminating project, I can talk about Module 3, the van der Waals equation and non-ideal gas behavior of the gases. What included in this lecture? First, we're going to do some review and introduction of van der Waals equation and non-ideal gas law, and also give some extension of the topic, which beyond the classes, and also some problems can be offered for us to practice. First, let's take a quick biography of the van der Waals. Johann Dietrich van der Waals was a Dutch scientist and worked on the molecular physics in 20th centuries and provided a great direct and fundamental to the modern physics and chemistry. He's also the winner of the 1910 Nobel Prize for physics because of his great contributions. There are so many laws and stuff named under van der Waals, like van der Waals molecule, van der Waals ratios, van der Waals forces, and van der Waals surface, and also different laws. All in all, he's a really great physics in the last century. The ideal gas law. What is ideal gas law? It's called the general gas equation, and is the equation of the states of specific ideal gas, and written like here. P times V equals to nRT. P is the pressure of the gas, V is the volume of the gas, N is the amount of substance of gas, N is a constant, and T is a temperature. However, the things are not always such ideal, especially when we want to calculate the compressibility of a certain gas. The compressibility is the capacity of something to be flattened or reduced in size by the pressure. It's written as that Z is equals to V over N over RT over P, and write as PV over nRT. As we just talked, the PV equals to nRT, so the Z should always be 1. Let's go to ideal gas. However, in the laboratory, when we calculate different kind of gases, things are different. As the pressure increases, the compressibility of a gas just decreases first and then increase a lot. For a certain type of gas and in a certain pressure, and the compressibility is also different when it's in different temperatures. So why this happen? Here we need to talk about the non-ideal gas behavior. Non-ideal gas behavior is a gas particles at atoms of infinitive size, and all have the measurable volumes. The intermolecular forces also affects a lot, which can quite strong between the certain atoms and molecules. The gas particles has a faint attraction for each other, and making the collision just become sticky and more complicated. The gas particles are surrounded by electron clouds also, which can be deformed or polarized. So all in all, non-ideal gas shows a deviation from the ideal gas law. Let's take a step back. So here we can see for 5 different gases, as the pressure increased and the compressibility increased also. When compressibility is lower than 1, so that means the Z is lower than ideal gas compressibility, which means the molar volume is lower than it should be. This can be explained as the attractive forces, like operating between the gas particles. They make them to pull each other, and it occupies some volumes. And also, when the pressure just increase, which means the particles just squeeze each other and repel each other a lot, so volume just become higher, and the compressibility become bigger than 1. When the gas is in the high temperature, which can be explained as the kinetic energy increase. The more kinetic energy they have, the particles move faster at the high pressure, and the repel forces just become more. So it makes the compressibility more than 1 ounce. So when the gas is in high temperature or in the high pressure, it's not going to be idealized. This chart shows some specific data of the Z factor as a function of the pressure and temperature for methane gas. To deal with a non-ideal gas, we need to introduce a van der Waals equation. It can be regarded as a transform of the PV equals to nRT, written as P plus A times N squared and over V squared times V subtract NP, and also equals to NTR. This part is a correction for the molecule attractions. A, the constant, corresponds to the strength of the attractions between the molecules, the forces between them. B is a constant that corresponds to the size of the molecules, and just like the volume of which. And this part is a correction for the volume of the molecules also, for all of the equation. In this chart, by comparing the different gases, we can see the difference of the A and the B. So as long as the quality of the molecule increases, so it's just take more spaces, the B just increase also. It's a little bit easier to understand. However, for A, it's not always obvious the quality of the molecules, because when you talk about the intermolecular forces between the particles to make A different. The intermolecular forces are the forces which mediate the interaction between the atoms or the particles, including the hydrogen bonding, ionic bonding, and dipole forces, and van der Waals forces, and etc. Let's take helium and ammonia for example. Ammonia particles is heavier than and bigger than the helium, so B is bigger, so obviously. For the A, because ammonia has more atoms to be made, and there are some hydrogen bonding made between the particles, so the A is absolutely higher than the A of the heliums. To accept the van der Waals equation, there are two more equations to calculate the non-ideal gas. The Rayleigh-Cohn equation and Pond-Robinson equation. Maybe we're going to use them in the future in some scenarios. So here let's take an exercise. The carbon dioxide gas with this mole at this temperature and occupies this amount of volume at 15 atmospheres pressure. So we need to calculate the pressure by using the ideal gas equation and the van der Waals equation. AB constant has been given for the van der Waals equations. Let's calculate the percentage deviation of each value. By using the ideal gas equation, V equals to 0.536 and NT and O have been given, and PV, for the reason that PV equals to NRT, P can be written as NRT over V, so it's a 57.1 atmosphere, and for the percentage of deviation, it's 57.1 subtract 15 and 7.1 over 15. It's 40.2%. In respect of van der Waals equation, P plus A N square over V square and times V subtract NB equals to NTR. So all in all, P is equals to 49.6 atmosphere, so the deviation is 0.4. The percentage should be 0.8%. Compare these two, that's much more better. All in all, in this lecture, we talked about the physics van der Waals and review the ideal gas and non-ideal gas, and take more explain about why this happened, what makes the gas non-ideal, and some more equations about calculating the non-ideal we're going to use in the future maybe, and also do some exercise together. Here is all for this lecture. I hope you have already understand all of what I talked. And thank you so much. Merry Christmas, young ones.